You've seen them in sci-fi for decades, right? These amazing, instantaneous tunnels through space and time. But what if they're not just stories? Right now, some physicists are trying to build a real bridge from that sci-fi dream to actual science. And let me tell you, the path they're on is way stranger than any movie.
So that's the big question, isn't it? Are these cosmic shortcuts just pure fantasy, or do the laws of physics actually secretly allow for them? To get to the answer, we have to start with the one theory that should have made them possible, but instead it pretty much slammed the door on the idea for almost a century.
All right, so to really get the solution, you have to understand the problem first. And the single biggest roadblock comes from the very theory that even gave us a hint that these things could exist in the first place: Einstein's general relativity.
Okay, so let's get one thing straight. A traversable wormhole is not a black hole. The classic model makes a huge distinction here. There's no event horizon, no point of no return. A wormhole has to be a two-way street. You have to be able to go through it and then come back.
So what does this cosmic highway actually need to look like, geometrically speaking? Well, at its narrowest point, what physicists call the throat, the walls have to curve outwards. The best way to picture it is like taking two funnels and joining them together at their skinny spouts. This flaring out shape, it's a hard rule, there's no getting around it. And that's what leads us directly to the problem. And right there, that's the fundamental conflict. That flaring out geometry demands a kind of repulsive gravity. You need something pushing outwards to hold the tunnel open. But according to everything we know from general relativity, all the normal matter and energy in the universe creates attractive gravity. It pulls things in. That rule, the one that says energy can't be negative, that has a name: the null energy condition.
So you're left with this impossible catch-22. To get the repulsive gravity you need, you have to have a substance with negative energy density. Physicists gave it a cool name: exotic matter. But here's the thing. It shouldn't exist. And for decades, that was it. Game over. That was the showstopper that killed the whole idea.
But what if we've been looking at this all wrong? What if the problem isn't the material we're trying to build it with? What if the problem is the blueprint, the law of gravity itself? This one radical question just blew the whole thing wide open.
This new approach, it completely flips the script. In a modified theory of gravity called FQ gravity, you actually change the equations of geometry. So now, even if you use perfectly normal, boring matter, the new rules of gravity themselves generate an effective repulsive force. It's like the rulebook for space-time is doing the heavy lifting, propping the tunnel open all by itself, no exotic matter required.
And you know what? The math actually works. When you use a pure F of Q model, you get a valid working wormhole solution. But, and this is super interesting, when they tried to just patch general relativity by adding a little F of Q flavor to it, the whole thing fell apart. The solution became physically impossible, and that tells you something huge. You can't just slap a Band-Aid on the old theory. For a wormhole to exist, gravity might need a completely new operating system.
Okay, so we've got a blueprint that works on paper. Awesome. But would the thing actually, stand up? Or would it just collapse if you so much as looked at it funny? The design now has to face a series of brutal stress tests. It has to survive the gauntlet.
So for this thing to even be considered a possibility, it has to pass three big tests. First, all the forces have to be perfectly balanced so it doesn't just instantly collapse on itself. Second, any ripples or sound waves inside it have to move slower than light. That keeps everything stable and prevents weird time travel paradoxes. And third, it has to be tough. It has to actively fight back and shrug off any little bumps or wobbles.
That third test, the perturbation test, that's the big one. And the entire complicated analysis boils down to this one thing: a concept called the effective potential. The easiest way to think about it is like a landscape. The shape of this landscape, whether it's got a bunch of deep valleys or if it's all smooth hills, that tells you everything you need to know about whether the wormhole is stable or not.
So, what did the math say? This was the make or break moment. After all the calculations, the results came in. The effective potential, that energy landscape, it's positive. Not just in one spot, not just at the throat,
It's positive absolutely everywhere. And what that means is that the landscape is all smooth hills. There are no dangerous pits or valleys for an instability to fall into and get worse. Any little shake or wobble would just be like a ball rolling on a hill. It would roll for a bit and then settle back down. So get this, the very same modified physics that holds the wormhole open also makes it rock-solid stable. It passed the gauntlet with flying colors. Okay, so if you thought that was weird, hold on, because this is where our story takes a sharp turn and connects with one of the most bizarre, most profound ideas in all of modern physics, the quantum world. There's this idea. It's called the ER equals EPR conjecture, and it is absolutely mind-blowing. It suggests that a wormhole, that's an Einstein-Rosen, or ER bridge, and a pair of quantum-entangled particles, an Einstein-Podolsky-Rosen, or EPR pair, are the exact same thing. They're just two different languages describing the very same physical reality.
I mean, what does that even mean? From the gravity point of view, you have a bridge, a tunnel through space-time. From the quantum point of view, you have an information channel connecting two particles. The conjecture says they aren't just like each other, they are each other. This is a radical idea. It suggests that the very fabric of space-time might be woven out of quantum entanglement.
And if a wormhole really is a quantum channel, well, you could use it for quantum teleportation. Now, this isn't Star Trek beam me up stuff. It's about moving information. So, imagine Alice has one end of the wormhole and Bob has the other. Alice takes a quantum bit, measures it together with her end of the wormhole, and then just calls Bob up or sends him an email with the result. Bob takes that info, does a little operation on his end, and bam, he can perfectly recreate the quantum bit that Alice started with.
So this all ties together beautifully, right? We've designed a stable, traversable wormhole that also happens to behave exactly like a quantum information highway. But there's one last hurdle. One final, crucial reality check we have to perform before we can even dream about finding one of these things. It's a really subtle but super important question. What happens when you actually use the wormhole, when you send that quantum information through it? Does that energy, what scientists call the quantum back reaction, does that break the very thing you're trying to use? Does using the wormhole cause it to collapse? And the answer is no. The model holds up. The calculations show that the energy from the quantum information passing through isn't nearly enough to mess with the structure. The whole system, the modified gravity, the normal matter, the quantum channel, it all hangs together. It's fully self-consistent. It works, which leads to maybe the most exciting question of all. How would we actually go out and find one of these things? See, a wormhole would look almost like a black hole, but not quite. It would bend the light of stars behind it in a very specific, unique way. Its shadow would be a slightly different shape. If it rang like a bell, it would give off different gravitational wave frequencies. Even the light from stuff swirling around it would look different. These are the fingerprints astronomers could hunt for.
So look, is this all just theory for now? Yes, but it's an incredibly solid and complete theory. It suggests that the laws of physics might not just allow for wormholes, but that they could be a deep, profound link between gravity and the quantum world. And that leaves us with this final amazing question. If our reality is truly woven from quantum information, what other impossible wonders are just hiding in plain sight, waiting for us to figure them out?